A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture we will discuss the logic gates. This lecture has been taken from the course outline of Introductory Electronics, having the course code of PHY201. The today's lecture is basically related to digital electronics, that is also the part of Introductory Electronic course. The basic objective from the today's lecture is to understand the logic gates. Meanwhile, we will also try to understand the operations of logic gates, and then in the end of the lecture we will implement the logic gates in circuits. We have some goals from this lesson. The basic goal is to identify the basic gates and then also describe the behavior of each of the gate. We also need to describe how gates are implemented in using transistors or different extrinsic materials, and then we will move towards the combination of basic gates in particular circuits that are mostly used in different circuitry, and then for each of the gate involved in that system we will try to elaborate three major things. One is the Boolean expression for each of the gate, the other is the truth table, and the last one is the logic diagrams. So all these three things are important to us, and we need to discuss these three things related to each of the gate. So how we can describe the behavior of gates in circuits? So three things are important as we discussed in the previous slide. The first thing is the Boolean expression. What we do with the we develop the Boolean expression using Boolean algebra, a mathematical notation for expressing the two-value logic gates. The other is the notation for each of the gate, that is actually the graphical representation of that particular gate in a circuit, and each gate has its own symbol that is normally used to identify that particular gate. And the last thing is the truth table for each of the gate. The truth table actually shows all possible input and their associated output values. So all the possibilities for each of the gates are described, and then we can discuss all the input in that, and then the outputs are also expressed. So let's come toward the discussion on all of the gate one by one. Basically in today's lecture we will discuss some of the well-known gates, that is the NOT gate, AND gate, OR gate, XOR gate, NAND gate, and NOR gate. So for each of the gate we will develop the Boolean expression, the truth table, and the logic diagram for that. So logic diagrams are actually black and white with the gates distinguished only by their shapes. So we use colors for emphasis, just for understanding. So let's come toward the NOT gate, that is actually a single input NOT gate, and all the gates use the binary number system. In the previous lecture we discussed the various number system, just like we have the binary number system, octal number system, decimal number system, and hexadecimal number system. In logic gates are in digital electronics, that is basically working on binary number system. So in binary number system we have two values, that is 0 and 1, 1 is used for switch on position and for switch on situation, and 0 is used for switch off situation. If you look toward the NOT gate, so NOT gate accept one input signal, and the outcome of that is that it gives us the opposite signal as a output. Just like if we have input as a 0, the output will be 1, and if the input is 1, the output will be 0. So the Boolean expression for NOT gate is just like x is equal to a dash. In the logic diagram we can see that the a is the input here and x is the output. So this is the basic logic diagram for the NOT gate. And in the truth table we can see two possibilities. The first possibility, a is the input, x is the output. If the input is 0, the output will be 1, and if the input is 1, the output will be 0. So this is some general explanation regarding the NOT gate. Now we are coming toward the AND gate. The AND gate is a bit different from the NOT gate because it accepts two input signal, and there is some condition for the AND gate. The general condition is that if both of the input signals has one value, then the output will be 1, otherwise the output will be 0. So this means that if any of the value among the input is 0, the result will be 0. So the Boolean expression is for AND gate is x is equal to a dot b, a multiplied by b. This is the logic diagram symbol for the AND gate. This is the input, a and b are the input, and x is the output. Here in truth table we have expressed all the possible input and the associated outputs. So if we have 0 and 0 as an input, two input signal, so definitely the outcome will be 0. If 0 and 1 are provided as an input signal, the outcome will be 0. And then if we have 1 and 0 as an input signal, the outcome will be 0. And if both the signal have the 1 and 1 value, then the outcome will be 1. So that is the AND gate of speciality, that it can gives us the 1 value when all the inputs have the 1 value. Let's come toward the OR gate. In the OR gate, accept two signals, but there is some condition for that. If both the input have 0 value, the output will be 0, otherwise the output will be 1. So this means if any one of the input value is 1, the output will be 1, otherwise if both the input values are 0, the output will be 0. So the Boolean expression for the OR gate is like x is equal to a plus b. This is the Boolean expression for the OR gate, and the logic diagram symbol for the OR gate is like a and b. This is x is the output for this particular case. So in the truth table we have 0 and 0 as an input, so the output is 0. So if we have 0 and 1 as an input, the output is 1. For 1 and 0, the output is 1, and for 1 and 1, in both cases, the output is equal to 1. So this is some information regarding the OR gate. This slide basically explains the XOR, that is the exclusive OR gate, and this gate also accept two input signal. And if you look toward this gate, this is actually the opposite of the if both this has the condition that if both are the same, the output is 0, otherwise the output is 1. This gate has the speciality that if both the inputs have the same signal, so the output will be 0, but if both the input has the opposite signal, the output will be 1. So this is something about XOR gate. If you look toward the Boolean expression of XOR gate, then in this case x is equal to a plus b, the logic diagram is a bit simple to the OR gate, but anyhow there is line in this particular case. So we have the logic diagram for this XOR gate. A and B are the input, X is the output. Let's come toward the truth table. In truth table, all the possible input and output are expressed. When the inputs are both the inputs are the same, the output is 0. When the inputs are different from each other, or maybe it's opposite to each other, so the output is 1. Again, when both the inputs are 1 and 1, the output is 0. So the XOR, that is exclusive OR gate, that is there is some difference between the XOR and OR gate, because it's only differ in one input situation. When both input signals are 1, the OR gate produces as a 1, while the XOR gate produces a 0. So this is a bit different between XOR gate and the OR gate. We are coming toward the NAND gate, and this slide will explain the NAND gate. The NAND gate accepts two input signals. Here we have A and B as the input signal, and X is the output. Here we see X is the output. So there is some condition for the NAND gate. NAND gate is actually the opposite of AND gate, and if both the signals are 1 and 1, the output is 0, otherwise the output is 1. So this means that if both the signals are 1, the output is 0, otherwise the output is 1. So if we see that if both the signal are is equal to 1 and 1, so the output is 0, otherwise the output is 1. So for 0 and 0 input, the output is 1. For 0 and 1 input, the output is 1. For 1 and 0 input, the output is 1, and only for 1 and 1 input, the output is 0. So we are discussing the NOR gate. The NOR gate accepts two input signals, and there is some basic strategy of this gate. The basic strategy of this gate is that if both are 0, the output is 1, otherwise the output is 0. So the Boolean expression for a NOR gate is X is equal to A plus B dash, and the logic diagram for this particular case is like A is equal to A or B is equal to that is X. So that is the logic. This is actually the logic diagram for the NOR gate, and the truth table is provided here. In the truth table, we have all the possible input and output. When the inputs are 0 and 0, the output is 1. When the inputs are opposite, 0 and 1, the output is 0. And similarly, when 1 and 0, the output is 0. For 1 and 1, also the output is 0. So NOR gate is actually just like not OR gate. In simple expression, you can also express the output of the NOR gate as a not OR gate, means that the results are the outcomes or the output from the NOR gate is opposite to the OR gate, or to the OR gate. Just it's exactly the same, like you can develop a NOT gate in front of the OR gate, so it will give us a result that is NOR gate. So we have the description of all the gates, and if we review the gate what we discussed before, then in simple words, the NOT gate inverts its input signal, and the input for the NOT gate is definitely 1. The AND gate actually produces 1 if both the inputs values are 1. If we have the OR gate, then the OR gate produces 0 if both inputs are 0. The XOR gate produces 0 if input values are the same, that is the XOR gate. The NAND gate actually produce 0 if both the inputs are 1, and the NOR gate produces a 1 if both the inputs are 0. So this is something about the NOR gate. So this is what we had discussed before, that are actually the gates with the single and double output. Just like if we have the AND gate, NOT gate that has a single input and single output, but here in the case of the the other gates except the AND gate, we have the 2 input and 1 output. That is something what we discussed before. So all the gate has the 2 inputs and 1 output. Now we are coming toward the bit complicated case where we have more than 2 inputs. So what will be the gates or the implementation of gate for that particular case, and what will be the result on the truth table? So definitely when the number of input increases, the possibility of output also increases, and all the possibility as well also increases, and that lead to the extension of the truth table. So the possibilities definitely increases for input and output as well. So this is the 3 input AND gate, for example, that produce an output of 1 only if all the input values are 1. So we have the truth table, logic diagram symbol, and Boolean expression for the AND gate that has the 3 inputs. So all the possibilities are provided in the truth table. Here you can see 0 0 0 1 0, and then 0 0 1 is equal to 0, and all are equal to 0 except when all the values are 1. So that is something about the gates with more than 2 inputs. So how we can develop the gates in circuits, and how we can implement that is a bit complicated question, but anyhow we need to address that, because we need to know how the gates are implemented in circuits, and what is actually the basics and benefits of the gates. So we use different semiconductor tool for that, and for the construction of gates, transistor, that is actually a device that is acting as a wire that conduct electricity, or resistor, or as a resistor that blocks the flow of electricity depending on the voltage level of an input signal. That is what we will be using. So a transistor has no moving parts, yet act like a switch, because it's acting like switch. In some direction it can allow current, while in some other direction it can forbids current. So it is made of a semiconducting material. If you look toward the transistor, we had very detailed lectures or view regarding the transistor, because we have different sort of transistor like BJT, that is bipolar junction transistor. We also discussed the unipolar junction transistor, and then in the previous several lectures we had also discussed the field effect transistor and metal oxide semiconductor transistor as well, metal oxide field effect transistor. So definitely the transistors that actually that is the interesting part of the electronics, and semiconductors are used for that, especially the extrinsic semiconductors are used for that. So the transistors are used for the constructing the gates. So how we can construct the gate? So for this purpose we need 3 things. One is the source, another is the base, another is the emitter, or that is actually typically connected to the ground. That is the transistors. So If the electrical signal is grounded, it is allowed to flow through an alternative route to the ground, where it can do not harm. So this is something about the simple application, simple working of the transistor. We have base, we have source, and we have emitter that is grounded, and the output is also obtained here. So this is a basic symbolic representation of the transistor. So how we can construct gates using the transistors? That was actually the last part of our lesson, that how we can utilize the idea to develop the transistors in a circuit. So for this purpose, the easiest gate to create are the NOT, NAND and NOR gates. Using transistor, how we can get the NOT gate, using transistor, how we can get the NAND gate, and then how we can get the NOR gate. So let's come first towards the NOT gate. If we come back toward the truth table, let's see the truth table of the NOT gate. This is the truth table of the NOT gate, because that actually inverts the input signal. If the input is equal to 1, the output is 0, and if the input is 0, the output is 1. So let's come how we can implement this in a circuit. So this is actually the diagram for the NOT gate, and the transistor is used for this purpose. Here we have two things, one is the input, another is the output. This is the input signal, this is the output signal, and it's basically inverts the input signal. And let's come toward the AND gate, and if you look back toward the AND gate, the truth table of the AND gate, that has the understanding that it can have 0 value in all cases when the values are input values are 0, or any of the value in the input are 0, so the result will be 0. While if all the values are 1, so the result is 1. So this is actually the truth table of the AND gate. So now we are coming toward the how its transistor circuit, that how we can get the NAND gate. So this is something about the NAND gate. You see, this is two input, W1, V1 and V2. These are actually input, and the output is obtained here. And the third one is the NOR gate. How we can create the NOR gate from transistors? So in this case we have two inputs, but that is connected to the base. This is the input to V1, and this is the input V2, and the output is obtained at V output over here. So it can be utilized as a NOR gate. How we can utilize this transistor in circuit? That is the most important questions of today lecture, and we have some combinational circuits, and the input values explicitly determine the output. Now for this purpose we have sequential circuit, and the output is a function of the input values and the existing state of the circuit. So we describe the circuit operation using the Boolean expression, the logic diagram and the truth table for that purpose. So this is something about the circuit and its implementation. So combinational circuit is the combined thing that is coming from the gates, and more than 2 or even more gates are utilized, and the output is expressed for this combination. So the gates are combined here, and this is the combinational circuit, and here we can the gates are combined into circuit by using the output of one gate as the input of another gate. So in this case we have input that are actually 3 input, and the output is 1, that is X. If we look toward the inputs, initially we have 3 input, that is A, B, C, and that is provided through gates, and the later on we have 2 input as well, that is D and E, and the final output is X. So in this way we have combinational circuit, and that is the combination of more gates. So if you look towards, we have several gates that are utilized here, and the output is accordingly manipulated. So for the combinational circuits, 3 input require 8 rows to describe all possible input combination. The thing become a bit complicated. So the same circuit using a Boolean expression of AB plus AC. So if you look toward the truth table, we have actually 5 input, that is A, B, C, D, E, and the single output that is expressed here. So in this way the combinational circuit has the complicated truth table. In this combinational circuit we have the following this expression like A into B plus C, and in this case 2 gates are provided, but we have the input signal as A, B, C, and then finally B plus C, and finally we have the output that is in the form of A into B plus C. So that is interesting because we can manipulate the output in this way. So this is for that particular combination circuit. We have circuit equivalent for any particular situation, and if you have 2 circuits that produce the same output for identical inputs, then the Boolean algebra allows us to apply provable mathematical principle to help design the circuit. Let's come toward this particular case where A into B plus C, that is equal to AB plus BC, that follow the distributive law. So circuit must be equivalent in this particular case, and that provide that particular law. So we have properties of Boolean algebra, and that is we have several properties that are found in Boolean algebra, and for AND gate and for OR gate. We have commutative law, we have associative law, we have distributive law. We need to identify the identity, and then we have complement, and then we have the Morgan law for that particular case. If we apply the commutative law in AND gate, so AB should be equal to BA. For OR gate, A plus B should be equal to B plus A. And associative law, 3 inputs are there. AB into C should be equal to B into C, A into B, BC. And in the same way for the case of associative law, A plus B plus C into A plus C should be equal to the A into B plus C. So this is actually the law that is provided regarding that. We have adders, that is actually the in digital levels the addition is performed in binary addition operation, and that is carried out by special circuit that is normally considered to be adder. We have also a separate lesson on adders because it's also part of our course. In case of adders, the result of adding 2 binary digits could produce a carry value of 1, just like 1 plus 1 should be equal to 1 0 in a binary number system. So we have half adders, that is actually a circuit that computes the sum of 2 bits and produce the correct carry bit. Now we have the carry and input. If all are 0, the sum is 0. If there are 2, so here we have no carry, and if both are 1 1, so this carry is equal to 1. So this is a simple adders. We have a circuit diagram representing a half adder, where we have the sum that is equal to A plus B, and carry is equal to A multiply B. The sum is this is actually provide the sum, and this provide the carry for that particular case. So we have several type of adders. We have full adder, we have half adder. So a circuit that takes the carry and values into account. So we have input, A and B are the input. This is carry in and this is sum and this is carry out. And B is the input, this is carry in and this is carry out. And this is the logic diagram of any particular full adders. So we have multiplexer, and in case of multiplexer, a circuit that uses a few input controls signal to determine which of the several output data lines that is routed to its output value. So this is something about multiplexer. So the multiplexer is a bit complicated, and that is actually not very much related to our course. So we have circuit memory, and that could be used, the logic gate could be used in circuit memory. So circuit memory is a bit complicated, and that is also generally discussed but not. So further implementation in the form of integrated circuit, that is also called as a IC, and that is normally used in electronic systems. So this is the simple diagram of the integrated circuits. So like especially used in CPU. So this is some discussion about the logic gates and its explanation. Thank you very much.